my screen?
Yeah.
Cool. All right, so thank you very much, everyone, for coming. My name is Ashraf. I joined the recommendation research team in September to work on Project 42, and I'm very excited to show you our work today. The whole team, and a special thank to the contextual record team who've been very supportive of the project throughout the last 6 months and beyond, really. So let's first anchor the problem that we are working on. So this is contextual Slate recommendation. So basically, we have a context. So for example, here we are on a tech website, and we want to recommend a banner of items. So on the right side, you can see a set of different recommendations for slates of size 2. What you see on top of the banner are the labels that we want to predict. So C bar stands for the probability of having no clicks. R1 and R2 are the reward for the first item and the second item, respectively. So there's a constraint here in our problem, and that is that there's at most one interaction with the banner. So a user will either ignore the banner completely or click on at most one item. And we see here, for example, that on the first banner, we have a good recommendation, a good contextual recommendation. We are on the tech website and we have tech-related products. The second banner, however, has a slightly worse recommendation with running shoes, and the last one has tennis balls with a phone and has a slightly higher probability of receiving no clicks. But there's more than just the product that we recommend that goes into understanding what a user, why a user might click on our banner. In fact, we might consider how big or visible the ad is, what's the layout of the ad, how many items does the banner has, but also how likely the user is going to be to click on the banner. Is this user really active based on their previous engagement? Is it an accidental clicks, which happens a lot on mobile because of the size of the device? And is the recommendation relevant based on the user's history? Maybe the user has visited that product in the past. And finally, the most used one, which is the affinity between the recommendation and the context, which is the reco signal, but it's really a faint signal. This is a signal that, based on our experience and on the data, is really secondary in explaining why a user might click. And we can really build a very robust probability of click model while disregarding this reco signal and only focusing on user engagement features and all of the above. And so based on that, we like to draw an analogy with the astronomer, which has a very similar context. And indeed, the astronomer is trying to get some good image quality of faraway galaxies. But in order to do so, they need to build a set of tools and understanding of local phenomena. They need to subtract the sky by building telescopes in specific locations of the world. They need to build an understanding and a knowledge of image processing. And they've built adaptive optics, all of that to have a better understanding of local phenomenon and improve their image quality. The same way we are trying to improve our recommendations by really understanding all these different layers that go into understanding and explaining why a user might click on our banner. And so the same way, we're considering the visibility and the slide layout, but also the user's past engagement features like the last visit, the history. This is what we call X. This is understanding the atmosphere. Also the item positions in the banner. Is the order, does it matter for the recommendation? Are there some winning combinations of products that are increasing the probability of click? And finally, the reco signal. That's the faraway galaxy. This is the very small signal that explains why your user might click. And that's the affinity between the context, omega, and the product recommendations, A1 to AK for Slate upsize K. So if we look at the equation and explaining the probability of a click based on the reco signal, that's the affinity between the recommendations and the context features, and using as also the user engagement features. As we said before, really the most important signal here to estimate this probability is X, but to build a recommender system, what we want is really to get rid of this, we want to subtract the sky, so we want to get rid of this user engagement features. So most recommendation system approaches will try to remove X from the equation, and so that is by integrating over this user engagement. So there's three ways of doing so, really. So the first one is the online reinforcement learning approach, which basically means to just try over and over again. This is a technique that we usually see in game AI with DeepMind and OpenAI, but that's not really suitable for Reco, as it might lead, it will lead to a lot of bad recommendations before getting any good. The second approach is the modeling approach. That's training a regression over the probability of click by using a parametric form of the relationship between X and the output that we look at. That's the probability of click. And finally, there's the Horvitz-Thompson estimator, which estimates the reward that we're gonna get from a recommendation. And that's very handy in case where the user engagement feature has a high dimension by using this balancing score. Now, if we want to use this recommendation system in production, it needs to be fast and it needs to scale. At Criteo, we have millions of items and we can't evaluate each of our items against the user's interest. It would be too slow, it's infeasible. But we have fast maximum product search algorithms such as FACE that allows us to get the arc sort of this matching, which is f of omega, the context embeddings, and beta, the product embeddings. So the inner product gives us the affinity between the context and the recommendations. And we want to draw from this arc sort the recommendations. So our recommender system, in order to be used in production with fast algorithms, needs to match that parametric form. So with the policy learning approach, this is easy because we start from this parametric form and we optimize F and beta. But with the modeling approach, our model parameters need to match this form. So if we look closer to this distinction between the policy learning and the reward modeling for a simpler case first, where we are only looking at recommending one item only. So we moved from the argsort to the argmax problem. In the policy learning, from bending feedback or the reinforced algorithm, unlike the reward modeling, this is already solving an argmax problem. It's only going to retrieve the best item based on the user's interest. So it has less parameters, which makes it easier to train. And because the argmax is not differentiable, we're going to use a softmax to relax the argmax. For the reward modeling, however, we need to assume a parametric form of the probability of click that matches the decision rule, the inner product of F and beta, and it requires a high parameterization to produce a strict ordering of the whole catalog. So we're not just retrieving the single best item, A, but we are really learning the full ordering of our inventory. And in fact, in reality, misordering high CTR items, the best items, will be much more costly than misordering the worst items. But our model have a different objective. It's maximizing the likelihood, and therefore it's using the capacity to retrieve the full ordering of the catalog. But now coming back to the initial problem of Slate recommendation, what we really need is an alloc sort and not an alloc max. So with the traditional policy learning approach, we saw that it's really solving an alloc sort problem. So to solve the alloc sort problem, we need to use the we can use the top K heuristic, which is basically spreading the mass over K items and retrieving the top K item instead of just the single best item. And in the case of the reward modeling approach, as we already mentioned, it's solving the alloc sort problem out of the box. And so we can just retrieve the top K items from the full ordering of our catalog. So just quickly to visualize what the top K heuristic does, if we look at the inverse propensity score approach on the left alone, we see that it's going to put the mass on the single best item. And on the left, we see a huge spike. And if we use the top K heuristic, now we see that the mass is spread over 2 items instead of 1. And this is because this IPS method makes the independence assumption, which basically means that it's going to recommend, it makes the assumption that the recommendations are independent. And so it doesn't forbid duplicates in our banner, which is a wrong assumption, and which we'll see lately hurt the model. So now we've seen that subtracting the sky, so removing this user engagement feature is a tedious task. And so we can take a completely different path and use a preference learning approach which will completely ignore this reward signal and only look at the ranking signal. So what does it mean? If we look first on the first banner with a microphone and a phone, and let's say that a lot of users click on the phone as opposed to on the microphone as opposed to the phone, the model will learn that the microphone is better than the phone. If on another banner we see a lot of users clicking on the phone rather than the running shoes, the model learns that the phone is better than the running shoes, and this way the model can learn a full ordering of the catalog without looking at the reward signal. So it's not a reward optimizing approach as opposed to the reward model. And our approach, the PRR model, probabilistic rank and reward model, combines both signals. So if we look at the full picture and try to model both the reward, so whether there was a click or not, but also the ranking signal, so the reward for each item in a slate, we have 2 components in our probabilistic rank and reward model. The first component is to predict the probability of a click or a non-click, to be more specific, C bar. So as we said earlier, to model the probability of a click, really the main signal here is the user engagement features. And so we have a nuisance parameter phi that try to model the probability of a click using the user engagement features or bidding features. Now for the ranking, to use the ranking signal, and as a reminder, we need to have a parametric form that matches our decision rule, the inner product of F and beta. And so we're going to use J and beta that are going to be equal to F and we're going to use, sorry, J and psi that are going to be equal to F and beta. These are just new notations that matches our final decision rule. And we also add position bias parameters, gamma and alpha, that, as we said, at the very beginning are representing the weight of whether the phone will be at the first position or at the last position. This will impact the probability of a click on this product. And also combining different items in a slate might influence the probability of a click on these products. So we can branch off from this model by either cutting off the ranking signal, and this will give us a reward model that only outputs the probability of a click or no click, or we can cut off the reward signal and get the ranking model. We also consider other baselines to experiment against our approach with policy learning, and more specifically, inverse propensity score approaches. So first we consider a Slate IPS that makes the assumption, again, as we said earlier, of the independent assumption that doesn't forbid for duplicates in our banner. And this method comes with very high variance because it fails to recognize the similarity between banners that might have all the same items, where just one item is different. And it's even more costly when the catalog grows. And so it fails to scale to millions of items. And to fix this this high variance problem from the Slate IPS, we can use the independent IPS, which again makes an independence assumption that is wrong by considering not the slate as k items, but breaking it down as k slates of 1 items. So here we can see at the bottom that the reward now becomes the sum of the reward of each item in the slate. But as we'll see later, is actually having some more robust results. So to recap, our PRR model combines both the reward and the rank signals to produce a strict ordering of the whole catalog. It is trained on all the banners, whether they were clicked or not, to take both the reward and the rank signals, but it requires high capacity to produce these calibrated CTR. The policy learning, which takes the banded feedback through the Horvitz-Thompson estimator, retrieves only the single best recommendation instead of the top k items. And so it will need the top k heuristic to solve our Slate recommendation problem. And it does not estimate the click probabilities. And finally, the preference learning approach, as we said, ignores the reward altogether and takes a completely different path. So how well did this work? First, we look at a toy example. So this is our whole inventory. This is a very simplistic example where we have only 7 products and 4 context categories. So we're looking only at 4 different types of websites, and we can recommend from a catalog of 7 items. The first thing we do is that we look at the calibration of our different approaches. So what we look at here is the probability of click as given by our models against the true CTR in the data set. What we see is that the PRR model is able to, a model that is calibrated and that has converged will ideally have points on the diagonal. This will mean that our model is calibrated, and we see that our PRR model is having some pretty good results and is calibrated. But the reward only model, which does not return the reward for each item in the slate, is slightly less calibrated. And finally, here we're looking at the Slate IPS estimate, and we see that it gives us very poor CTR estimations.
excuse me, any idea why you have such horizontal lines on your IPS? Like it seems it's constant. You have only 4 possibilities of estimated CTR.
Yes, we think that this is because well, first the problem is very simple, and so we don't have many products, and the data set is very finite. So we guess that if we increase the size of the data set, this will eventually converge to a diagonal.
I think it's to do with being like 1 click, 2 clicks, 3 clicks, just because of the you're not seeing a lot of the data set is quite finite. We probably should dig in a little bit more to completely clarify exactly where this is, but it certainly does converge to the correct thing if you have more data.
Okay. Well, it's definitely not the most central aspect of the presentation.
It's maybe worth mentioning
it was out of curiosity.
the Slate IPS is a lot worse than the IIPS here. But IIPS sort of maps you down to a single action, which is not what we're seeing here. This is a two action example.
Thanks.
So now if we look at the CTR for different recommendations, so as we said before, we know in advance the best recommendations for each context. And here we're looking at just 2 contexts, sports and tech. And if we focus on sports, for example, where we know that the best recommendations are running shoes and tennis balls, we see on the top right that if we look, for example, at A1 equal running shoes, the second best items should be tennis balls. And here the orange dots are the true CTR estimates, and so they reflect the best recommendations. So the higher the CTR, the better the recommendation. And we see that for the best recommendation, our PR estimate in green is very close to the true estimate, which will lead to better recommendations. But the reward only, which does not return does not predict the ranking rewards, the reward of each item in the slate does not perform well and will lead to bad recommendations, as we see. For example, for the running shoe example, we see that if A1 is equal to running shoes, the best estimated action is going to be to recommend a phone as opposed to tennis balls on the top right panel. Now, if we look at policy learning approaches, for the CTR, as we said previously, for the independent IPS approach, all the mass is put on the single best action. So for a sports context, the best recommendation is running shoes. And so we see a huge spike that here is cut off, but really the mass is all on the single best item, which is running shoes. And so to spread this mass over the top K items, we can see in blue the top K independent IPS that puts the mass. The first big spike is still the duplicate running shoes A1 and running shoes A2, and then the second one is the best recommendation running shoes and tennis balls. But we see that a lot of the mass is on duplicates because this method does not forbid the duplicates in the banners. For the slate, which already looks at slight recommendation, we see that it has poor estimates of the true CTR, which are in black, and does not really benefit from the addition of the top K heuristic. Now, after looking at this, we ran some simulated A/B tests. So basically, we had a model of the user's behavior, that's the oracle, And we simulated we simulated a data set from this oracle and a uniform policy. And then we trained all of our baselines on that data set. And then we ran a simulated A/B test on all these baselines. So basically we created a new impression. We drew recommendations from all the different baselines, and then using this oracle again, computed the reward for each model, which gave us finally the CTR for each baseline. And here we see that with the very simple toy example that pretty much all the baselines are performing fairly okay, which is a validation of the protocol. But then moving on to a more realistic setting where we have 1,000 products and slates of different sizes from 2 to 18. And if we first zoom in on the ranking model, which is the preference learning approach, as we said, this preference learning approach compares the items in the banner, and so it will benefit from bigger slates as it will show more comparisons. So if we click on a banner of size 18, we can compare this clicked item with the 17 other items. So we see that the ranking model is actually performing very well on very big slates, but it's not performing well on slates of size 2, and it's not even relevant for recommending just one item. On the other side, we have the reward model, which is the opposite, where it performs very well on smaller slates, but is hurt by bigger slates because it does not look at the ranking signal. The rank signal is just optimizing for reward. And finally, we see that the PRR model is performing very well across all these different slate sizes, but also that the top K IIPS in this case is also performing very well. However, if we scale and increase the number of items in our catalog, we see that at first with 1,000 products, again, that the top K IPS is performing very well. But then as we increase the size to 5,000 and 10,000, now the IPS methods are performing very poorly, and the PR approach is the best one as it borrows strength from both the ranking model and the reward model. And so it's able to scale and to give good recommendations across all these different settings. And finally, if we go even beyond and use 1 million products, the PRR model keeps giving good recommendations. And if we look at a speed benchmark, it's even clearer that the IPS methods are hurt from scaling the catalog, as it's 20 times slower to train, even though it's only looking at clicked banners, which account for only 6% of the data set. And we can also notice that the ranking model, which gave us some pretty good recommendation overall, is very fast, 2 times faster, as it's also only learning on 6% of the data set, so only on the click banners. So to conclude, our contributions are on this new PRR model, so probabilistic rank and reward model, which is a reward optimizing model that produces better slate recommendations at scale. And as we explained, it enables maximum inner product search for fast recommendation in production. And we've used a flexible simulated A/B test protocol to run these experiments, but we would like in the future to run experiments on real data that will hopefully confirm these results and showcase the performance and scalability of this approach. Thank you very much. So if you have any questions.